I hope everyone's doing well. I'm Mr. Ish. Thank you for joining me here for this differential equation application problem, and we have to solve it. It's dealing here with the second order differential equation. As you read it, you're seeing here that a mass is suspended by a spring and it undergoes vertical oscillations. The displacement is your x variable given in terms of centimeters of that mass over time, your t variable in seconds. If at time t equals 0 seconds, we have a displacement of 1 or 6 centimeters, we have to find the amplitude and we have to find the period. And this right here is our starting information. We have a second order differential equation, half d square x divided by dt square is equal to minus 48x. You have a certain mass which is suspended and it looks something like this. Here's my mass. And you know this right here is your equilibrium position. If you were to pull it down and let it go, it would start oscillating, or if you were to squeeze it up and let it go, it would start oscillating, and you would see that there will be two positions of maximum displacement. You would have one position here and one position here as this thing goes back and forth. This right here is your maximum positive displacement, this here is your maximum negative displacement. But from the equilibrium position, looking up or looking down, here's your positive amplitude, here's your negative amplitude, your maximum displacement. But in all instances, amplitude is always in absolute value, so it's always a positive outcome in terms of your result. But that's what you're looking here in terms of your amplitude. Period also has to be determined. If you think back to your pre-calculus years, you had an equation d was equal to a sine or cosine, and then you had a variable wt. This was your lowercase omega variable, which played into your frequency and your period determinations. Your omega variable, time, amplitude, your displacement. Four variables: displacement, your amplitude, these two variables in their unity, your lowercase omega, and your time will give you your items you need with regards to the period and the frequency. But this is what you're thinking about, sine and cosine and this equation. Your amplitude is coming from here, your displacement is coming from right here, and this is what we're talking about, except we're looking at everything here with regards to differential equations. So let's look at this. If I'm looking at this and I multiply everything by 2, what am I really doing? I have a d square x divided by dt square is equal to minus 96x. But what type of differential equation is this? Is this homogeneous or non-homogeneous? Look at your variables x and x. You know your x variable here is giving your displacement. It's your dependent variable. You would see this on your y-axis. And you know the time over here is your independent variable. You would see this on your x-axis. Your x is synonymous with your y, your t is synonymous with the x and the y that you're normally accustomed to seeing, but here we're seeing x and t. This is my y-axis variable, this right is my x-axis variable. When I'm looking at this, if I were to push this on the other side, I'm looking really at something which is d square x over dt square, which is my second order derivative, plus 96x is equal to 0. When I look at this, I know I'm dealing with a homogeneous differential equation, not inhomogeneous, where a certain function is linear, because a certain function is really indeed equal to 0, it's homogeneous. This is what I really have. So this is what we'll work with. If you rewrite that differential equation in a more easier format, what you really have in terms of your question is this. You have x double prime plus 96x is equal to 0, and that's what we will solve, and then this will give us our period and our amplitude. How do we solve this? You know, when you're looking at a second order linear homogeneous, you're thinking about this, x is equal to e to the rt. Your first order derivative is equal to r e to the rt, and your second order derivative is r square e to the rt. You have to bring these items in because you see them over here. When I do so, I have r square e to the rt plus 96 e to the rt is equal to 0. If I were to isolate the exponential terms, bring them out, take them on the other side, divide them by 0, they'll go away. I really have r square plus 96 is equal to 0. R square is equal to minus 96, and r is equal to the square root of minus 96. When you do it, what are you getting? 96 is a 16 times 6, and I will come out. I have a I for root 6, but I can show you that in a better way. I really have, if you think about all the possible solutions, positive and minus, you really have something which looks like a plus and minus bi. Complex conjugates are coming out as your solutions because you don't have real solutions in here, you have complex conjugate solutions. A plus and minus bi here will be synonymous with 0 plus and minus I 4 root 6. Now you know a is equal to 0, b is equal to 4 root 6, and there's a certain template we have to bring our solutions when you have complex conjugates coming from second order linear homogeneous differential equations. What is that basic template? Your basic template is as y is equal to e exponent ax. Then you have a constant a cosine bx. Then you have another constant b sine bx. The lowercase a and the b are representing that complex conjugates. The uppercase are arbitrary constants which you are dealing with. Simply because you have a second order differential equation, you must have two constants. Even if a constant is 0, it's still a constant. And yeah, this is what we have. But if you look at it in terms of the variables we have, what we really have is x is equal to e exponent at, and then a cosine bt, because now our variables are really x's and t's, not y's and x's, plus b sine bt. And if I bring everything into play, what do I have? I have here x is equal to, this right here is my solution of this differential equation right here. X double prime plus 96x is equal to 0. I know a is 0, I know b is a 4 root 6. The I you're not worrying about. E to the power of 0, it goes away, it's a 1. Then I have a cosine 4 root 6 t. That's part of it, and then the rest is b sine 4 root 6 t. And here is my solution for your differential equation. X is equal to constant cosine 4 root t plus another constant sine 4 root t, and we're good. Now let's determine our period. We'll do the period determination first, then we'll worry about the amplitude. Amplitude is very easy. When you look at the period, you can look at it from right over here. You have a certain item over here in terms of a formula. Period is equal to 2 pi over b, but b item is right over here. You're doing here 2 pi, and the period can be symbolized as a capital T. 2 pi over 4 root 6. When you compute this, you have a pi over 2 root 6. You can convert this into a decimal answer. I won't, but this right here is your period, and it will be correct. Remember the equation I was giving you at the very beginning, displacement in a simple harmonic motion is equal to a sine or cosine. I'm just putting sine or cosine, and it was omega variable in the time. This right here is giving your period, and it will give you your frequency. If you were to reciprocate this, your frequency can be determined, but we don't have to do it. We're doing period and amplitude. Our period is determined coming from right here, and it's correct. Now let's determine our amplitude. To determine our amplitude, we're looking at that information right over here. At time t equals 0, we have a displacement 1 over 6. And you plug them right over here. At time t equals 0, I have a displacement 1 over 6. And I'm doing a cosine time t of 0. 4 root 6 times 0 is the cosine of a 0, plus b sine 4 root 6 times time 0, because there's my 0 is a 0. Sine of 0 is a 0, and goes away. And when I solve this out, cosine of 0 is equal to 1. I know a is equal to 1 over 6. When you take these parameters and you bring them here into this equation, you solve only for this because b was equal to 0. When you plug in your value, you're looking at x is equal to a, which is determined to be 1 over 6. A is equal to 1 over 6 because cosine of 0 is a 1. 1 over 6 cosine 4 root 6 t, and this right here is your equation. Because the sine component went away at time 0, sine of 0 is 0. And you know this looks very much like that equation I was giving you earlier. D is equal to amplitude times cosine times an omega variable and time. This right here is your amplitude, so you know your amplitude is 1 over 6, and that right here will be correct, and it's done. What's your shortcut way of determining the amplitude really fast? Right here. At time t equals 0, when your system is at rest, you already have a displacement you're seeing, meaning you're seeing a maximum displacement, and that displacement you're seeing at time 0 is your amplitude. How can you picture that in a graphic manner? I'm erasing this right over here because you know what your solution is. You can rewind back, but I want to show you this graphically. When you're looking at this equation of this right here, d is equal to a cosine wt, your omega and time, when you look at it graphically, you know at cosine of 0 you have a certain displacement. You would have something which is looking like that, and your amplitude is determined. If this was d, your displacement is equal to a sine, where you're looking at a sine, you know sine goes to the origin. At sine 0 you have 0, and you'd be looking at something like this where displacement is none. There is no displacement, meaning your system is at its equilibrium position. With the cosine at time 0 you have a 1 over 6, means your system is already in a displaced position away from the equilibrium, and your mass was up over here by 1 over 6 units or 1 over 6 centimeters. In case if it was a sine, your mass was at the resting position, equilibrium position, where the displacement was equal to 0. Here the amplitude is 0, but you would have an amplitude develop here or over here. And you know that right there is your shortcut. Just by looking at 0, 1 over 6, you know my amplitude is 1 over 6. But I've shown you how you determined it from your differential equation. You solved it, You plugged in your parameters, you determined your constant turned out to be your amplitude, and there it is, 1/6, period pi over 2 root 6, and we're done. Thank you for watching.